Hi, everyone. My name is Cynthia Brosque, and I'm a product manager at SafeAI. I'm really excited to be presenting today our safety framework to assess autonomous construction and mining equipment. SafeAI is a startup based in California, and we retrofit heavy machinery to make it autonomous, both for construction and mining uses. As we know, the motivation for us, artificial intelligence, is going to transform these industries and by providing a safer, more productive, and reliable environment to work on. But as the industry is evolving, we want to incorporate more autonomy. Obviously, the need for having a comprehensive safety framework as we deploy these technologies on site is really important for the innovators in the field and the operators. In this paper, we introduce SafeAI safety framework and the workflow that we developed and follow across our global projects. And we highlight these applications through one of our examples. As we mentioned, obviously, safety is integral to the development of autonomy. And this not only comes at the software level, but also on the operational side. We have a vehicle agnostic solution that integrates a reusable hardware package into existing fleet of vehicles. And we developed all the software for autonomy, which is proprietary even from the operating system app. And so when we look at the kind of traditional safety framework that exists, they kind of focus on the component failure from the bottom up type of approach. But we have based our safety framework around the system theoretic process analysis, which is short for STPA, which was developed by MIT in order to consider not only the component failure, but also starting from the system interactions, how it also behaves in collaboration with the human factor and considering more complex dynamic processes. And because of this, this framework has been deployed already in aerospace and other industries that are more complex, and as an alternative to the bottom-up analysis. And so our idea of deploying this framework starts from incorporating safety really early in the process, where the flexibility to change the design to incorporate safety is higher, and also the cost is lower to make changes based on safety. And as we move to development and production phases, we will, of course, also kind of follow the functional safety, more traditional analysis. And then, of course, throughout utilization, we also introduce layers of protection analysis, which is a third layer of our safety framework, which has to deal with all of the residual hazards that were assessed throughout the process and how we deal with that on the grounds. And that has to do a lot with the site change management, traffic, operations, and regulations as well. So when we looked at kind of this three-layer method, we start kind of building from STPA methodology, then the layers of protection as we deploy, and then finally also the component level functional safety requirements. So all of these three will fit into our software kind of requirements, assessment, verification, and validation process with our QA teams. So how this works, starting from the STPA process, first we define the use case. So in our scenario, this is a load hold dump cycle with a retrofitted vehicle. Then we establish very clearly what is the operational design domain. So under which conditions the vehicle that is autonomous has been tested and approved to be functioning with, what could be the the presence of like other agents, people, etc. And usually we start each deployment at the tightest boundary possible, and we keep increasing as we pass out several milestones. We also map possible interactions between the vehicle and other equipment, the environment, and humans. And that leads us to identifying losses. So, of course, what are the undesired or unplanned events that could result in injury or getting like a near injury or a collision. It could also be at the system level, for example, losing data. And once we know what are the things that obviously we want to avoid, we try to understand from the use case perspective, what are the types of control actions that could lead us to that unsafe state. So for example, perhaps an action that is required for safety wasn't provided, or was not provided in a timely manner, or was stopped too early. For example, if it was a braking action that is not applied long enough. And that leads us to defining the first kind of hierarchy of safety requirements. So we want to understand from these unsafe control actions, we come up with requirements to avoid this. And then as a second layer, we try to identify, okay, if this unsafe control action happened, what is its cause? So what made the system behave in this way? Perhaps it was, okay, the perception system had this kind of occlusion, so why did that happen? And so that causal analysis leads to a second layer of safety requirements, and like that we can keep decomposing the system into the most kind of fundamental levels, even of the algorithms that we use. Of course, as I mentioned, we'll also do the typical functional safety at the component level, looking at probability of failure and the likelihood of the detection of the failure for typical like hardware components. And then we incorporate several protection layers, which all have to be independent of each other. And this comes with like the site regulations. How do we manage the operational layers when we are at a real construction or mining site? And this can also include like traffic management, having a remote stop of the system to be able to avoid the hazards that we identify. Obviously, the most effective risk mitigation strategies are always to be able to remove physically the hazards. So the idea of being able to remove the person from inside of the cab of the vehicle is really powerful, and kind of that's the philosophy behind the autonomy. And from these three layers, we specify all of the safety requirements which go into our V model of development for validation of the software through module testing, integration, and then finally the validation. And the way we do this is first starting in simulation testing of first like subsystems, then entire systems, then conducting repeatable tests in our proving grounds, and then we go into like kind of that closest ODD boundary where we control a lot of the variables and the environment, and then finally to the final production deployment. And this is also our way to scale globally as we deploy in different sites. Overall, of course, safety for SafeAI is in our DNA. It's not only in our name, but it also comes from our philosophy and the way that we design the system. And we want to be able to deploy applications that run in really uncertain environments with multiple agents and also humans. So really safety is paramount, and that's why we kind of enforce this three-layer safety methods. That is a very systematic way for us to assess the hazard of our operations. So we're really excited to be working on this space and to continue to contribute to the heavy equipment autonomous ecosystem that has already been delivering safety improvements in mining for a long time and more recently in construction, while also unlocking productivity benefits. Very happy to answer your questions. Feel free to reach out to us, and thank you again for the opportunity to present today.